Hello, I'm Dial Holton, Microcalorimetry Product Manager at TA Instruments. I would like to welcome you and thank you for joining us in today's webinar. Our presenter today is Dr. Malin Sirkusk. For the last 9 years, Malin has held a position of Product Manager and Application Specialist at TA Instruments. She holds a Master's of Science degree in Biochemistry from Stockholm University and a PhD from the University of Lund in the laboratory of Professor Ingemar Wadzo. She has worked extensively with differential scanning calorimetry and isothermal titration calorimetry, as well as other biophysical methods. Her early work in microcalorimetry instrumentation development included responsibilities in product management, application laboratory management, and marketing at Thermometric in Sweden. She is considered the world's leading expert on the TAM isothermal instruments, with numerous microcalorimetry publications, and in October of 2014 was recognized for her contributions to the field of microcalorimetry and featured as a biophysicist in profile by the Biophysical Society. The title of her webinar today is Introducing the TAM IV, the new multi-channel microcalorimetry system. Malin?
Thank you, Dial. So today I would like to introduce to you the new TAM IV, the new multi-channel microcalorimeter system. TAM IV is unique and universal. It's flexible and modular and stable and sensitive, which I will show you example of during the presentation today. TAM IV is a unique microcalorimeter system. It's the world's most sensitive, stable, and flexible microcalorimeter system. It is completely modular, combines the highest heat flow sensitivity with unmatched long-term temperature stability to measure processes that are undetectable by any other technique. The flexibility of the TAM IV thermostat, coupled with the available calorimeters and accessories, creates a powerful analytical tool suitable for any laboratory and offers performance and sample throughput that is unmatched by any other isothermal calorimetry instrument. On the pictures below, we can see on the left-hand side the standard TAM IV instrument, which has 4 positions for 4 different and individual calorimeters. The picture to the left is a TAM 48 channel, which is a high throughput calorimeter where up to 48 independent calorimeters can be installed. TAM IV is the new generation TAM. Taking the best from its predecessors, we have now created an even better with new features in the TAM IV thermostat. It has new and more responsive temperature control, provide rapid thermal equilibrium and extended temperature range. It goes down to 4 degrees for real-world cold storage applications. It goes between 4 and 150 degrees C. New plug-and-play calorimeters will allow for fast and easy installation. It has high-speed USB to PC communications, a new accessory interface box with capacity for 8 different individual modules to be connected to the system. A new module is available for interfacing up to 3 independent probe sources or sources, such as a pH probe or a light source. TAM Assistance is still the software to use, and it has new features for instrument control, data acquisition, and data analysis. Microcalorimetry is a universal technique. It's a technique for the direct measurements of heat production or consumption from a sample. And as virtually any chemical and physical processes will result in either heat production or heat consumption, we will be able to measure most any processes. Calorimetry will quantify the amount and rate of heat release in terms of heat flow, heat, and heat capacity. It's a non-specific technique, making it ideal for study almost any kind of processes within the biological, physical, and chemical field, within life science, material science, and within the pharmaceutical field. So, isothermal microcalorimetry. The heat production rate is directly related to the rate of the reaction. It's also the heat production rate that we measure. This is expressed by P, which is the heat production rate. It's equal to the enthalpy of the reaction rate, and a function of the concentration of the sample. The heat flow is related to the heat production rate and is plotted on the plot to the left. Heat flow is measured in watts, which is joules per second, hence that is a rate, so it's a rate-sensitive technique. Heat flow is plotted versus time, and the rate of reaction can be read at any time of the plot, which is seen on the left. If we integrate the data, then we get a total heat produced, and that is related to the extent of the reaction, which can be seen on the right-hand plot, also plotted versus time. TAM IV is a universal tool with a universal technique, and it could be used in almost any application area. This slide will show an example of a few applications that the TAM IV can be used for. I will go into detail of some of the applications in the next coming slides. TAM IV is used widely within the pharmaceutical science, where the applications will include stability of a pharmaceutical ingredient, compatibility of a pharmaceutical ingredient and any excipients. It could be used for looking at polymorphism, amorphicity assessment. An amorphicity assessment is the example shown in this slide, where an amorphous lactose is put into an ampule, where also a small microhydrostat is put in with a saturated salt solution that will give a certain relative humidity over the sample. The amorphous part of the lactose will absorb the humidity, and we can see that in the plot. Up to 40 minutes in the plot, we can see the heat of absorption of humidity to the amorphous regions of the lactose. Once enough humidity is absorbed, we induce crystallizations of these amorphous parts, and we see that in a highly sharp crystallization peak in the plot. Once the crystallization is finished, the signal will return to zero. If we integrate this curve, that will give us an idea of the amount of amorphous content within the sample. This application is not only restricted to relative humidity with water. It could also be used with other solvents if that's what the sample needs to absorb to be able to induce crystallization. TAM IV is also widely used within the material science field. Again, applications will include stability, compatibility, just in the same way. It could be used to follow curing, reaction kinetics, safety assessment, hydration and swelling reaction, absorption. It's also used for looking at battery efficacy and battery stability. In the example here, it's a measurement according to a Stanag method where safe storage of a propellant is tested. It needs to qualify if a propellant can be stored for up to 10 years. So what you do is you put your propellant into a closed ampule, put it into a temperature between 60 or 90 degrees as described by the method, and measure for the amount of days that's also described for that particular temperature. The square you see in the plot, that's wherein the heat flow of the sample must stay to be safe for these 10 years. It needs not to exceed the higher heat flow limit at that temperature. TAM IV can also be used within the life science, where applications include isothermal titration calorimetry, where you can characterize binding reactions between proteins and ligands and other macromolecules. It could be used for microorganism detection, possible identification, and growth condition optimizations. It could be used to study small animals and living tissues within the microcalorimeter. It could also be used to evaluate drug effects upon living cells. Also biocompatibility. For example, if blood components are compatible with, for example, dialysis membranes. The example shown in this plot is 3 different types of bacteria where it's clearly shown that they grow with a completely different profile. The interesting thing by looking at microorganism detection is that you can start with only 1 colony-forming unit to start with, but because they are replicating, even if one bacteria will produce very little heat, while they're replicating, there will be more and more, and at some point you will have enough bacteria in the sample to be able to get a detectable heat flow. Again, if we get back to this overview slide, we have talked about the amorphicity assessment, propellant safety and stability, which is a standard method, looking efficiency of stabilizer for different materials, but battery efficiency, microorganism detection, stability of pharmaceutical or other materials. It's used for ITC, material compatibility, and polymorph. And this is just a few examples what you can use the microcalorimeter and the TAM IV for. So if we summarize the benefits of using microcalorimetry for the study of different properties of materials or living cells or pharmaceutical substances, it is universal. If anything is happening in a sample, it will likely be detected. You do not need to define the response you expect before the measurements. It's non-specific. Everything goes on in the sample will be detected. It's not necessary with sample preparation, even if you can prepare the sample to get more specific measurements. It's non-depending on the physical state or the shape of the sample. Anything that could be fitted into the sample handling system can be put into the calorimeter. It's non-destructive, which means that after the measurement, you can do further analysis of your sample. It's direct and continuous, giving you real-time data. It's highly sensitive. Measurements can be performed at or close to ambient. There is no need for accelerated conditions. So that was an introduction to microcalorimetry and what microcalorimetry can do. But the TAM IV is the instrument that will do this for you. It's a very flexible multi-channel microcalorimetric system. Depending on what system you choose, you can have up to 48 individual and independent calorimeters. You can have nanowatt up to milliwatt sensitivity, depending on which calorimeter you choose. Sample sizes could be from less than 1 milliliter sizes, 4, 5, up to 20 milliliter, and finally 125 milliliter sample sizes, depending on the calorimeter. The sample handling system and the accessories will add possibilities to add and mix samples, perfuse gas or liquid over a sample, control or continuously or stepwise change the relative humidity or gas or liquid composition over a sample, measure pressure changes at the same time as the heat flow, dissolve a solid sample, and also add additional probes for increased specificity. It's one system with multiple possibilities. TAM IV is a modular calorimeter system. And the base is the TAM IV thermostat. And as you saw in the beginning, we have 2 different thermostats, one with 4 positions for 4 different type of calorimeters, and one with 48 positions for up to 48 mini calorimeters for high throughput measurements. So the thermostat is where you put your calorimeter, and functionality and measuring capacity is obtained by adding different type of calorimeters, sample handling systems, which we also refer to as the ampules, and any auxiliary equipment that you need. I will go through every step of these modules in the next slides. To be able to measure very sensitive and during long periods of time, you need a very good thermostat. And that we have with the TAM IV thermostat. It's a liquid-based oil bath system, and continuously circulates the heat sink medium that will prevent any external disturbances from the room, or if there is a very active reaction, but that will not alter the temperature of the thermostat with this control of our thermostat that we have. The temperature regulating system utilizing the state-of-the-art electronic thermistors. It's sensors that detects the temperature but also used to constantly adjust the heating and cooling and the oil flow speed, and that will give us a temperature drift over 24 hours that is less than 100, plus minus 100 microdegrees C. The thermostat offers multiple temperature control modes to characterize different thermal events. The most common use of the TAM IV or a microcalorimeter is isothermal, where we keep the temperature stable for long periods of time and follow sample what happenings over that time. It's also possible to operate in step isothermal mode, where you load the sample at a lower temperature, measure at that temperature, increase the temperature to the next temperature without reloading the sample, and measure how the reaction rate increases with increasing temperature, for example. The TAM IV also have the power to measure the heat flow during the temperature change itself, so we can see if a transition is induced during that change of temperature. TAM IV can also operate in a slow scanning mode, which means that we scan extremely slowly, 2 degrees per hour. With that slow scanning rate, we can have a very high resolution of any thermal events that occurs very close in temperature to each other. And we also ensure that bigger samples stays in thermal equilibrium during the measurement. So once you have the thermostat, you need to equip it with different calorimeters. The calorimeter for TAM IV is shown here, and most of the calorimeters are heat flow calorimeters, which means that we measure heat flow out from a sample. It's a passive measurement, and we follow the reaction whenever it happens. We just wait for the heat to flow out of the calorimeter. The most sensitive calorimeter we have is the Nano Kilometer. It has can measure up to 5 milliliter sample sizes. All our heat flow calorimeters is also twin calorimeters, so it has a sample side and a reference side. In the reference side, we put an inert reference that will match the sample by heat capacity as good as possible, and that will minimize the noise of the system. The Nano Kilometer has an accessible reference, so you can optimize the reference to match your particular sample very well. That's also why you get a very high sensitivity of that calorimeter. The microcalorimeter can accept up to 20 milliliter sizes. It is also a very sensitive calorimeter, and it has also an accessible reference. These two calorimeters, the most sensitive calorimeters for 4 and 20 milliliter sample sizes, occupies each one position in the TAM IV thermostat. To be able to have high throughput microcalorimeter measurements, we need to minimize the physical size of the calorimeters, and that is done with a mini calorimeter that's seen on the middle of the screen. That calorimeter is also a twin calorimeter. It has a reference, but the reference is mounted beneath the sample. So we have a sample over the reference design of these calorimeters, which means we can occupy much less space in the thermostat and get more calorimeters into the system. This reference is not changeable by the user. So this is more used for routine and standard measurements, where you choose the reference upon making the choice of your mini calorimeter, and you use that reference throughout your measurement. The mini calorimeter, which is seen there, is mounted in what we call a multi-calorimeter. In this picture, you have an assembly of 6 4 milliliter mini calorimeters that sits together, and this 6 mini calorimeters will fit one position in the TAM IV thermostat. This 4 milliliter mini calorimeter is also the calorimeter that is used in the TAM 48 channel TAM IV thermostat. Also, the 20 milliliter calorimeter is available in a mini calorimeter design, and in this case, 3 calorimeters can be mounted together in a multi-calorimeter, and one of these 3 20 milliliter calorimeters can be mounted also in one position in the TAM IV thermostat. For very big samples, up to 125 milliliter, we can offer the microcalorimeter. It also have the design of the sample and over the reference, but in this case, the user can open up the calorimeter and optimize the reference to match the sample they are going to measure at this time. The microcalorimeter is also occupying one position in a TAM IV thermostat. These are the heat flow calorimeters of TAM IV. To the outermost right, we have another type of calorimeter, the precision solution calorimeter or the precision titration calorimeter. That is a semi-adiabatic calorimeter where we are not measuring heat flow, we are measuring temperature differences. This calorimeter works by having a sample of interest in a small ampule within that reaction vessel you can see with the blue liquid in. And that small ampule can be pushed down to a small rod in the bottom and crushed, so a solid or liquid sample comes out in the whole 100 milliliter vessel there and is dissolved, and we measure the heat increase or decrease while this sample is dissolving in the liquid. The precision solution calorimeter also occupies one position in the TAM IV thermostat. Looking at the flexibility of the TAM IV, even if the Nano Kilometer is the most sensitive calorimeter in absolute terms, it has much less sample size. So depending on how much sample you can use, the relative sensitivity of the calorimeter could be bigger for the microcalorimeter than for the Nano Kilometer if the sample, depending on the sample volumes that is used. So depending on sample size and the sensitivity needs, different calorimeters can be used. You have now the thermostat, you have the calorimeters you have chosen, now you need to put your sample within something, and that is used with the TAM IV sample handling system. We offer a complete array of ampules in 2 basic types, the closed ampules and the open ampules. Closed ampules, also referred to as static ampules, where we just put in the sample within the ampule, close it, and we do no manipulation with the sample during the measurement. Just put it in the calorimeter and see what happens with the sample. The open ampules are part of the microreaction system, where you can directly manipulate or modify your sample or the surrounding of the sample during the measurement to be able to change the relative humidity or perfuse a gas or liquid or inject something into the sample. To be able to use the microreaction system, you need maybe a syringe pump, mass flow controllers for controlling the relative humidity, and that is controlled through the accessory interface. The new accessory interface will control up to 8 independent accessories as the mass flow controller, peristaltic pumps, syringe pumps and stirrer control, and also the new voltage in-out module. That module can supply or measure voltages for up to 3 independent probes or sources. It could be accessories such as a user-configured pH probe or a light source to induce a reaction inside the calorimeter. If we look at examples of the different measurements here, the static measurements, as I said, anything you can fit into an ampule can be measured at. Static measurements are used mainly for stability, where no manipulation of the sample is going on, compatibility between components, which can be done by measuring each component individually and then measure the combination of the components and see if there is excess reaction that could come from any incompatibility or reactions between the components. It could be used for looking at reaction kinetics, where kinetic models can be fitted to the heat flow data. For looking at amorphicity, as I mentioned earlier, polymorphism, looking at curing, safety assessment, microorganism growth, etc. The example shown here is a stability measurements where they have increased the temperature of the same sample at different measurement. So we start at 50 degrees. We can see that the heat flow signal is very flat, but it's still offset from the baseline, which means that we are measuring a very slow reaction. By increasing the temperature, we are increasing the reaction rate. So 60 degrees, still flat, but a little higher, so there is more reaction going on. At 70 and 80, we also get curvature because now the reaction is so fast, so we're actually consuming sample during the course of the measurement. For the titration setup, with the titration ampule, there is possibility for adding and mixing sample during the measurement. That could be used for looking at binding affinity, stoichiometry, and thermodynamic, the typical ITC application. Looking at complex formation, critical micelle concentration determination, looking at enzyme kinetics, mixing enthalpies, dissolution kinetics, absorptions, reaction kinetics, swelling. Could also be used for looking at drug effects on living cells. The example shown is a typical ITC experiment where you have a protein inside the reaction vessel, which you can see on the picture to the right. A solution, a stirrer, it should be a stirred solution, and a small cannula coming down where you can make injections in aliquots. So one injection is made, signal is coming because of the reaction, and it goes back to the baseline. Then the next injection is made, and we can see the cause of saturating the protein with whatever ligand we are injecting into the system. So from this experiment, the binding affinity, stoichiometry, and the enthalpy of reaction can be calculated. With the perfusion ampule, gas or liquid perfusion experiments can be performed. This could be done to look at stability under different atmospheres, looking at compatibility also under different atmospheres or with different solvents that continuously perfuse through the system. Looking at absorption, reaction kinetics. It could use for oxidation reaction studies, safety assessment again, hydration, swelling, metabolism of living small animals. With the perfusion functionality, you can always provide fresh medium to a living system. The perfusion ampule could also be configured with titration possibilities by injecting and mixing. On the right-hand picture, there is also what we call the matrix cartridge. If you have a powder and want to get a liquid or gas pushed through a powder, it could be contained in this matrix cartridge, and the gas can be guided through that and come out in the bottom of that matrix cartridge. The example here shows an example of an oxidation reaction. It's a polymer that's put in a perfusion ampule under two different atmospheres. The blue line is the oxygen atmosphere, and the green one is the nitrogen, the first 4 days it's under study. We can see on the oxygen there is a big reaction, and on the nitrogen, after the initial disturbance, the signal is at 0, so there is no reaction going on. After 4 days, gases are switched between the two channels, so the sample that was under oxygen now is under nitrogen, and we can see the reaction is going back to 0 immediately. The nitrogen sample now has oxygen after the switch, and we can see that we're actually turning the oxidation reaction on by adding this gas. So this is one way of using the gas perfusion ampule. A special version of the perfusion ampule is the relative humidity perfusion ampule, or the RH perfusion ampule. It can be used for morphicity assessment, polymorphism studies, compatibility, stability, absorption, reaction kinetics, again, safety assessment, hydration and swelling. And this works by adding 2 gas lines into the system. One is completely dry, going into the reaction vessel in the bottom, and 1 gas line goes through 2 humidifying chambers that's seen in metal in the middle of the RH perfusion ampule. In the humidifying chamber, the gas flow, the gas, nitrogen mostly, is humidified to 100% relative humidity. And then by controlling the 2 gas flow, the dry and the wet gas going in, we can regulate the relative humidity over the sample in the reaction vessel. The examples show again a lactose sample with amorphous region, where the red curve is a constant linear ramp of increasing relative humidity over the sample, and the blue line is the sample heat flow from the sample. At 1, that's where the sample starts to absorb humidity. Once it's absorbed enough humidity, at 2, we have induced a crystallization reaction. We get a peak. Crystalline lactose does not hold water, so the water that was absorbed is now expelled, and that's in 3, where we have an endothermic reaction where water is expelled from the sample. And then increasing the humidity even more, we will have a polymorphic transformation at 4. And we can follow the whole process. Dissolution. Dissolving a solid sample, or a liquid for that matter, can be done in 2 ways in the TAM. Either with the solution calorimeter, the precision solution calorimeter, as mentioned before, where you can see a little closer here, a small ampule sitting in the gold propeller, and the small tip where you push the ampule to crush the ampule to get the sample out in solution, and measure heat temperature increase or decrease upon dissolution. It is also possible to measure heat of dissolution in the microsolution ampule. It's a 20 milliliter ampule that fits into the 20 milliliter calorimeter of TAM, where the sample is then loaded into a small cartridge that's loaded into this ampule, and on the plungers in the top of the microsolution ampule, these small cartridges can be injected into the liquid and measure the dissolution of the sample. The microsolution ampule will only accept solid samples. Using the solution or dissolution calorimeter or the microsolution ampule could measure heat of dissolution or heat of wetting. It could be used to assess amorphicity, polymorphism, looking at dissolution kinetics, for example. The vacuum pressure ampules can be used to measure simultaneous pressure and heat flow during a measurement. Many energetic materials that are unstable also produce gaseous product during their composition, and with combining the measurement with the pressure, we can follow both the pressure increase and the heat flow at the same time. It could be used for study any gas-producing reaction. It could be used for safety assessment. It could be used for study absorption of gas or gases in a sample. It could also be used to induce a reaction by pressurizing a sample to be studied in the calorimeter. In this example, we have followed the simultaneously increased in pressure at the same time as the heat flow. The red curve is the heat flow of an unstable percarbonate, sodium percarbonate sample, and the red line is the pressure increase while the sodium percarbonate decomposes. With a 125 milliliter calorimeter, the macrocalorimeter, large and heterogeneous samples can be studied. It was mainly designed, or initially designed, for study batteries up to D-cell size batteries, but it can also be used for study any large samples that doesn't fit into the ordinary 20 or 4 milliliter calorimeter. It could be used in environmental science where you need to have big samples to get representable sampling of your sample. You also need a certain atmosphere over the sample, so you need both the sample and the atmosphere to fit into a certain volume. Also for food application, where whole pieces of food can be put into the calorimeter and studied. The example here just show different soils from different fertilizing and see how the bacterial growth, the microorganism in the soil will grow differently depending on which type of fertilizer they have got over time. I mentioned battery testing. There are two ways of do battery test in the TAM IV. It could be either done with a microcalorimeter, as seen as the calorimeter to the left, where there is a battery insert with a battery inside the calorimeter. That's for the bigger calorimeters, but for smaller calorimeters, the 20 milliliter multi-calorimeter or the 20 milliliter microcalorimeter can also be used. Microcalorimetry is the only method that will directly measure the occurrence of any non-current producing reactions under load. It is also a very sensitive method to directly assess self-discharge. Sometimes it's the only method because it needs the high sensitivity. It is a non-destructive method, so the batteries could be further analyzed after the measurements, and it's simple. Put the battery inside the calorimeter and measure at. The picture shows self-discharge of a lithium-ion battery inside the microcalorimeter. By adding additional probes, by using these new voltage in-out modules, we can add specificity to the method. Because any probes that you can fit into small miniature probes that could be fitted into a microreaction system. It could be a light source, a pH probe, an oxygen probe, any ion selective probes. It's also an example of a small UV vis detector that could be put into the calorimeter to add specificity to a method. The example shows simultaneous measurement of heat flow and chemiluminescence of a polymer that is oxidizing. Chemiluminescence will only measure the light emitting step in an oxidation reaction, while the heat flow or the calorimeter will measure all the reactions that goes on. This is why we have a little shift of 50 minutes of the curves. But it's essentially the same reaction, just that it's different parts of the reaction we are studying here. And I mentioned in the beginning that the TAM IV has a new extended temperature range, 4 to 150 degrees. And why are we so excited about the subambient temperature? Because now it will offer more opportunities for measuring microcalorimetric on sample subambient. Biological and ecological sample may be studied now directly at applicable temperature conditions. We can do assessment of kinetics and Arrhenius kinetics at lower temperatures. Food and freeze-dried pharmaceutical formulations can be studied directly at their storage conditions, at storage temperatures. And for many samples with glass transition temperatures near ambient temperature, it's now possible to study stability and kinetics below the glass transition. The glass transition temperature is an important threshold, and the stability profile can be radically changed above that temperature. For battery performance, we can do stability measurement at subambient temperatures now, and that's important as many batteries are stored or operated at lower temperatures. And also, lower temperature will reduce the reaction rate. As you've seen in the other example, we were increasing to increase reaction rate, but for some reactions where the reaction rates are very fast, it's beneficial to reduce the reaction rate so we can actually study the reaction in the calorimeter. And also reactions that have short induction times can now be measured accurately and with reproducibility. To summarize the benefits of isothermal microcalorimetry is that it's non-destructive and it's non-invasive. You can study any kind of process, it's chemical, physical, and biological. It's not depending on the physical shape of the sample. Whatever you can fit into the calorimeter, you can study. Solids, liquids, and gases can all be studied. There is no need to modify the sample in any way. You don't need to immobilize it, you don't need to chemically derivatize it. There is no need for sample preparation. It is completely non-specific, so if there is anything going on in the sample, you will detect it. And microcalorimetry continuously and directly measure the process under study, so you get real-time data from the process when it's happening. To summarize the new features of TAM IV is the new temperature range, 4 degrees to up to 150, improved thermostat design for enhanced calorimeter signals, the plug-and-play calorimeters for fast and easy installation, high-speed USB to PSC communications, the new accessory interface box with capacity for up to 8 different modules. The new voltage in-out module can interface up to 3 independent probes or sources. There is no longer a requirement for UPS that was for the TAM III, and a new TAM assistant software to provide new features of the TAM IV. So TAM IV, I would say, is the ultimate tool. It is the microcalorimeter system for the widest range of applications and the easiest sample setup and experimental configuration. It is equally useful in research laboratories as in industrial laboratories, including pharmaceutical production control. With the universal nature of the TAM IV measurements, it brings unique features and benefits. With up to 48 independent and parallel measurements, a unique application experimental setup flexibility, and unmatched long-term temperature stability and unsurpassed calorimeter sensitivity. This powerful platform is supported by the internationally recognized sales, service, and applications team of TA Instruments. So, if you got interested in this, please contact your local TA sales manager or email microcalorimetersupport@tainstrument.com. Thank you.
Thank you, Malin, for that informative presentation. A recorded version of this webinar will be archived and available online through the TA Instrument website. We will now begin the question and answer segment of the webinar. And again, I'll remind you to please submit your questions through the Q&A window. We will do our best to answer as many questions as possible.
Malin, there were several questions that came in during your presentation, and one of them referred back to ITC. And it asks us, what is the sensitivity of the ITC in the TAM IV with respect to what kind of binding content range can be measured, what kind of concentrations and volumes are used, probably comparing them to the standalone instruments that are typically used for biological samples.
For the titration in the TAM, we will not have a sensitive titration as we would have for the more dedicated ITC instruments that is available. I would say you can measure a few tens of microjoules is the detection limit for a TAM ITC. Depending on enthalpy of the system, you can still determine binding affinity down to tens of nanomolar, but again, it depends on the enthalpy of that particular reaction you are studying. Volumes, you have flexibility volume using a TAM ITC. You can use from maybe 500-600 microliter of liquid up to 4 milliliter liquid, depending on which ITC system you choose with the TAM.
All right, thank you. Malin, there's a question here about operating at subambient temperatures, and this has to do with how does it actually do that? As you get down below ambient, you get below the dew point, you have to worry a lot about condensation on cold pieces of metal and that kind of thing on samples. How does the TAM IV actually do that when it comes to operating down at those lower temperatures?
If you would operate below the dew point in the laboratory, there where the TAM is situated, we do offer an optional low temperature kit where we have inlets for a dry gas, either nitrogen or dry air, that could flush the plumbing of the TAM and the top plate above the thermostat to avoid condensation to critical parts of the instrument. And also when you load sample into the calorimeters, we need to make sure that there is no humidity coming down to be able to condensate inside the calorimeters, because it will mess up your measurement. So there will be a perch ring above the thermostat, above the calorimeters, that will create a dome of dry air while opening the calorimeters. So we will dry the ampule before it goes into the calorimeter to avoid condensation inside. This dry air dome is just open when a sample is loaded into the calorimeter.
Here's a specific question about a calorimeter, Malin. There's a question that comes in that says, what is the minimum volume required for a nano calorimeter?
We have measurements where applications where you can use a few milligram of sample, but and then you can use up to a full ampule with several grams of sample. It will completely depend on which type of reaction you are studying. If we want to look at crystallization of amorphous parts, it's enough to put in 10, 20 milligram of a sample into the calorimeter because the heat is so cooperative when it comes, so you get a sharp peak anyway. If you're studying very, very slow reactions, then you would like to get up to maybe gram amounts of sample to be able to study those slow reactions.
What about the volumes? If you were looking at liquid samples or something else, what kind of volumes or minimum volumes?
Again, it depends on what you want to study. For a closed ampule, you can use hundreds of microliter of a sample. Looking at an epoxy curing, we use a liquid epoxy in before it starts to cure. It's tens of microliter is enough to be able to detect the reaction, while for maybe a liquid formulation where you have very little of an active component in, you might need to fill the ampule with maybe 4 milliliter or 3.5 milliliter to get a detectable signal. So again, it depends on the type of reaction you study.
There was another question that came in on the actual hardware of the thermostat and the calorimeters. How easy or how fast can you actually change a calorimeter in a TAM IV? Whether you're removing it or swapping it out, changing calorimeters, what does it take to actually do that?
If you would need to reinstall a calorimeter or to change it, the actual change will not take very long time. I think you would do that in less than an hour. The thing is that when you have changed the calorimeter, it needs to stabilize at that temperature because we are controlling the temperature very stable. The calorimeter has a big heat sink and all that needs to come into the same temperature throughout before you get stable baseline. And after, both by changing temperature and installing new calorimeters, for the mini calorimeters, we recommend a night, overnight, to stabilize it. For a nano calorimeter, it may take you 24 hours before you have a stable, because all the temperature needs to be equilibrated inside the thermostat.
Right.
But the actual change doesn't take that time.
Another question just came in, and with all of the different measurements that are made in a TAM IV, different calorimeters, different samples that can be made. Can you describe a little bit of the advancements and the kind of analytical tools that are in TAM Assistant now that will help with all these measurements?
TAM Assistant software is as TAM IV itself. It's like a modular. We can put in new modules and new features for analyzing depending on what we want to look at. TAM Assistant will be able to analyze and handle signals from this new what we call the I/O module, where we can connect different probes. We can collect those signals and use that to correlate that with our heat flow to analyze them together in TAM Assistant now. There are several features in the analysis software to allow analysis of different kinetics and Arrhenius kinetics. It could be used for analyzing Stanag applications. There will be more features added to the software after time, depending on the general request that comes for a different type of analysis necessary.
Okay. Here's another specific question for you, Malin, that has to do with a specific measurement. And someone is asking if you could maybe describe an example of measuring dissolution kinetics. We can respond later on to this question with some data or something, but can you just sort of describe how you would measure a dissolution kind of experiment and measure the kinetics?
The kinetics for dissolution. If it's dissolution kinetics, we would recommend the microsolution ampule in the 20 milliliter microcalorimeter to do that to start with. And then you will inject the solid sample into the solution. And since we are measuring the rate, we can follow the dissolution because there will be heat produced during the dissolution process, so we can follow that over time. And we measure rate in microwatts, so that's joules per second, microjoules per second. We follow that, and that rate can be fitted, that reaction can be fitted to different models of calculating the kinetics of these processes.
Right.
There are some processes, some kinetic modules already in the software, or if there are other models, you can easily export the data out to bring it into other type of software you can have for analyzing kinetics.
All right. Malin, you mentioned several techniques where you were inserting probes potentially down into separate probes down into the sample while you're measuring the heat flow. You measure pH or oxygen levels or whatever might. How do you actually get the probes down into the sample? Is the hardware already configured so that you can insert it down in? How do you actually get the probes down in the sample?
There are microreaction systems that have an auxiliary inlet, a little bigger inlet, so it will fit a miniature probe. And there are also slots where you can guide the cables out from this microreaction system. So we have titration ampules and perfusion ampules with these auxiliary inlets to be able to put probes into a microreaction system. We also have static ampules with access holes and ampule lifters with holes to be able to have cabling down into the calorimeter. The probes themselves needs to be configured by the user today as we have it, but there are routes available how to take the cabling up from the reaction vessel in the calorimeter.
Well, thank you, Malin. That was a very interesting seminar on isothermal calorimetry, and a lot of nice questions submitted from the attendees. I want to thank all of you for being with us today and the time you spent and submitting questions. If any additional questions come up, please feel free to contact us at any time through the support hotlines and direct emails that you might have for us. We'll be glad to answer the questions, any questions that you might have. And again, once again, thank you for your time today, and hopefully we'll see you again at another TA Instruments webinar. Thank you.
Thank you.